So I'll be talking about geological model, the workflow, on how to do it. So basically, in the oil, what part now? In the oil industry, we have different sections. So the part I'm actually talking about is like more the technical parts, where you can like build geological models to like estimate what volumes you have in place in a particular field. So for this, it's just a short presentation on how to, on the steps that you take to build a model that you can actually use to estimate these volumes that you have in a field. So, so these are the different steps. First of all, what you do when you want to build a model is you think about the data that you have available, and then not just the available data, you have to know what to do. That's what you call the synthesis with that data that you have. So basically you have the data, and then you do like a geological study. There's a regional study done already in the area that of interest. So you read up, it's called literature review. So you read up so that you know the sedimentological environment, the stratigraphy of the area that you're working on. So you just basically do like a rundown of what you expect to impute in the model that you're about to build. So, and when you've done all that, then the next thing now is to go ahead and to build the model. And there are different softwares that you can actually use to do that. But basically what everybody uses now in the oil industry is Petrol. So for this context, we are going to be using Petrol to build a 3D static model. Because we're talking about the static model. We have different models that we can actually build to do this kind of thing. We have static model, we have dynamic model. But basically for the geologists, when you're starting up, it's called a static model because you still have all the data. You've not changed anything in the data. But for the dynamic model, that's basically what the software engineers do. They put the production data, historical data, and then they now use that to forecast what a particular model can actually produce in future. But for this context now, we're just looking at the static model, what you have originally. You've not changed anything in the data you have. So you just basically want to know what this field that we are looking at, what it has. What does it contain? Is it profitable? Is it economical to actually invest? Because the oil industry is not just about acquiring fields. We need to know where the money is. It has to be a lucrative kind of thing. You can't just go and they say you're drilling a well. To drill a well is like up to $1 million to drill a well. So you have to know what you're dealing with. So the static model kind of gives you an idea because you don't know what you're going to, when you are in there, what you're going to find. It kind of gives you an idea of what you expect when you actually drill a well and then you start production, etc. So, okay, so after you build a static model with construction, you kind of give the model you're building, you give it a structure, as in it's kind of a body. When you're building a house, it has a kind of a skeletal framework. So you give it a structure, how's it going to be? Does it have faults? In this field that you're looking at, does it have faults in play? And how are you going to include that fault in that model you're building? So, and then you also have to consider what you call property modeling. Property modeling is done after you build your grid. You have to impute, things inside to actually help you estimate this volume that we're looking at. So after the property modeling, you now do a volume estimation. And luckily enough for me, she has already talked a little bit on uncertainty studies. So those are the different steps you go through while you're building a geological model. So this is just an example of the kind of data that you expect when you want to build a model. Okay, so first of all, you have seismic data. What I mean by seismic data is most times the seismic acquisition. Okay. You have seismic acquisition. There are different steps in seismic acquisition. You go to the field and you get data, and then after getting data, you do a seismic processing. Then you now come down to seismic interpretation, and that's where we come in. Seismic interpretation, you interpret the particular area of interest. When you interpret the particular area of interest, you now use that. That's what I call the seismic interpreted horizons, and that's what you're going to use to impute into the model you're going to build. So after that, the next thing there is the well data. You need seismic data, you need well data, and then you also need interpreted well log data. Those data actually helps you to build the static model, and at the end of the day, it helps you to interpret the volume in place. And that's what is called the stock tank oil initial in place, that's STOI. So when you have that, and you have a huge STOI, when you do your initial estimation, people will say, okay, this is a profitable field. We can actually invest in the particular field we're looking at. So this is an example of, this is an example of the well log extracts. So here we have the gamma ray. Gamma ray is a type of well log that when you're drilling a well, there are kind of important logs that you need to take when you're drilling a well. The important ones are the gamma ray resistivity, the neutron density, because those are the important ones that will help you estimate whether you actually have hydrocarbon in place in a particular. This is the gamma ray. What it does is it kind of measures the radioactivity in the formation. Thank you. In the formation. So when you have high radioactivity, that's where you have mostly the shell, and then when you have low radioactivity is the sand. So it helps you determine your sandstone, and then the resistivity helps you in when you have a high spike in the resistivity. It shows that there's a presence of. Okay.
Go ahead, because we'll read just while the line goes on.
Okay, so when you have a high spike of this, which is the resistivity, that means that you have presence of hydrocarbon. And then the neutron density, let me see if I can find a good one. It helps you to know where you have presence of gas and oil. So when you have like a big balloon of the neutron density forming together, that means you have gas there. But when it's a bit leaner, it's oil. So these three logs are important when you want to build a geological model. So, and then the other one, you have the RFT data. RFT data are mostly pressure points. You take pressure points. Those pressure points also helps you in fluid contact determination. What I mean fluid contact determination is where you have the oil-water contact or the gas-oil-water contact. So those ones, they are very important in estimating where you have volume of oil. So, okay, so for well deviation, it shows you whether the well is a vertical well, or deviated, or horizontal. So those are the things that you need. Core data is important because when you have core data, that means you have like actual data from the formation, and it helps you to determine the permeability, the porosity values, and then when you're doing your estimation, because the geological model is mostly a statistical kind of thing. You have data at point places. You don't have wells, because it's from the wells that you actually get data, and then you don't have a lot of wells. But when you have core data helps you to kind of constrain your distribution. Like if you have from core data, you have porosity value of 0.23, and then from the well also, you have something similar, 0.25, like 25% of porosity. And then when you do your statistical run, you're getting values that are not are within those two values. That means there's something wrong with your estimation. You have to go back. So core data is important to constrain the distribution of your. If you have core data, it's an added advantage, but sometimes it's not so much available because taking a core from a well is very expensive. Okay, so then well markers. This is an example of well markers. And it helps you to distinguish between each formation because you have different sands. So it helps you to kind of, group your. It helps you to distinguish each of the sands that you notice along the well. And then also helps you maybe if you want to correlate it to another well, it helps you to, kind of make a distinction between the top of formation, base of formation, and then it continues like that until you get to, where you don't have anything around the well. So this is just an example of what you're going to get when you build a geological model, as in combining all these different levels together into a grid, into a whole grid. So just an example of that. Okay, so for static uncertainty, I'm just going to run through the workflow. She did dynamic uncertainty. So what you do for static uncertainty, because you're dealing with data that is not changing, you have mostly data that is not changing is net gross. It's coming from the well. The porosity is from the well, and some other data that you have gotten from your well, maybe from the RFT, from the core, etc. So when you have all that, and you have also the interpreted horizons, when you get your seismic data, you pick a particular horizon, you have that, you have the structural uncertainty is mostly for calculation of what you call the GRV. The GRV is gotten from fluid contact. So when you have the fluid contact and you have the horizon, you have like a particular area that you know that you have hydrocarbon. That's what you call the GRV. Sometimes when you do your interpretation, it's not so clear on the section. So you might have like a plus or minus 10 meter difference, so you can run an uncertainty on that. So those can be your uncertain parameter. Then for your Fashi model, what about Fashi is the properties you have within your reservoir. It varies. So it's uncertain. You can't actually say, okay, I have sand here, I have shale here. So it varies at some point. And when you run a statistical model, it changes. So those are the parameters that you could choose to run an uncertainty on. So net gross, the porosity, the net porosity, and the water saturation. So what you do is when you have picked your uncertain parameters, you now kind of generate. You generate a 1P and 3P. That's the high case and the low case for each of the parameters. You can do it in Petra or any other. There's an uncertainty workflow there that you can actually follow to do this. Okay, so you calculate the impact. Sometimes the impact, if you look at this is called the tornado chart. You use this impact to say, okay, yes, my Fashi is actually very uncertain. There's something I have to go and check here. It's not, you go back to the model and you work on it. So, and then at the end of the day, when you're sure that you have fixed the uncertain parameter that you're looking at, then you generate a high case and a low case, and you can use that in running the dynamic uncertainty. So at the end, in conclusion, it's used to estimate the volume placed in the field, which informs helps in planning and economics. Thank you. So any questions?
Please go back to the slide where you mentioned about markers. The well markers, please.
Okay, on well markers, the well marker is setting as, it's almost like setting as your seismic interpreted horizons, but this time you're placing it on the wells. Do you understand? You have the top of the sand. You call it a well marker, top of the sand. When you have a gamma ray, and you notice that there's a reduction in the radiation the activity and then you're looking at it, you know you're in sand. So you can pick that okay, this is the top of my reservoir, that's called the well marker. And then we want to distinguish it from the other ones below, because there can be different packs of sand along the well. So the base of it is what you call the base of the sand. So those are the well markers. So you can actually have like 2, 3, or 4 formations and sandstones in a particular well. So your well markers helps you to distinguish between those sands. And then it helps you also to correlate to another well. When you look at the shape of it's called the motif. The shape of what it looks like when you look at the curve, and you say, okay, this particular curve is looking like what I'm seeing in another well. Because you have a top and a base, you can use that top and the base and correlate to the other one and say, okay, this is the top and the base of the same sort of sand that I'm seeing in this other well. Do you understand?
Okay, just like an addition to what we asked. I want to say that it could be something like a thick shield that is continuous across the wells in your log.
Okay, that's called the maximum flooding surface. You can use that to correlate. The maximum flooding surface can be used to correlate across different reservoirs. That can also be a well marker. Use it to distinguish, because the maximum flooding surface is something that cuts across like the whole region. So you can use that to act as a well marker.